right, welcome everyone to the TIPE 2022 technology track. I'm Amy Elliott. I'm the North American host for the technology track, and I'm a researcher in 3D printing at Oak Ridge National Lab. So our first speaker today is Miranda Moschel. Miranda started her career in the world of powder metallurgy, where she worked in both traditional and press and sintered powder metal manufacturing, as well as 3D selective laser melting. From there, she moved to work at Xerox as a metallurgist on the 3D printing team focused on liquid metal jet printing, a novel 3D printing technology. Her work focuses on the development and improvement of the aluminum alloys produced on Xerox's flagship LMX printer. I've seen this printer in person. It is very impressive. So I'm excited to hear Miranda's talk titled "The Science Behind Liquid Metal Printing." All right. And we have our wonderful tech ambassador, Abby, who is helping us today. And let's just see. There we go. Here's Miranda. Hi, Miranda. How are you?
Hi, guys. I'm really excited to be here.
Awesome. Well, I'll leave it to you then. Thanks.
Okay, I'll go ahead and share my screen. All right, so thank you, Amy, for the introduction. As she said, I'm going to be talking about the science behind the liquid metal printing on the LMX platform from Xerox. And this is kind of the agenda I'm going to go through today. First, I'm going to talk a little bit about who I am and why I'm on this stage, and hopefully why you guys should be listening to me. And then I'm going to talk about where liquid metal printing sort of fits in the industry map today, because it is a novel technology. And then I'm going to step through and talk about the printer overview, because some of you guys may have seen this printer, some of you may have not. But this is kind of what it looks like on the right here. And then I'm going to start getting into some specifics behind the mechanism of magnetohydrodynamics, which is a mouthful, but we'll get through it. And then I'm going to talk about what the LMX printer actually does and what we produce. And then I'll be happy to take some questions from there. So just an introduction, as Amy said, my name is Miranda Moschel. I have a background in material science engineering, and I started my career in traditional press and sinter powder metal manufacturing. So people who are familiar with it, they know it's a sort of mass production method of manufacturing. So the scale is quite different than what we're used to dealing with additive industry. But it did give me some valuable experience dealing with the nuances of powder metal, which carried over into my first introduction to additive manufacturing, which was via selective laser melting. Right now, I'm working at Xerox as a metallurgist. Ironically, our printer does not use any powder feedstock. We use a wire feedstock, but hopefully this provides a little background and context for where I'm coming from as I explain these things. So I do want to talk about the industry a little bit. I'm sure you guys have seen graphs like this before, going through all the nomenclature and jargon of different printing technologies. And over here on the right is sort of the metal additive technologies that you guys are familiar with, selective laser melting, e-beam, all the big names you're familiar with. And then, over on the left, we have material jetting, which is not typically metal. This graphic specifically says there's only one metal printer that does that. And in reality, the technology I'm going to be discussing is somewhere between these. So we are material jetting, additive manufacturing technology, droplet on demand. So it's kind of a newer branch. So as far as the history of this technology, I just want to frame it a little bit here. It was really only 10 years ago in December of 2012 that the idea of using magnetohydrodynamics for liquid metal drop-on-demand printing was even born. So this is a very early technology. And it was later in December of 2018 that Xerox acquired that technology. So some of you guys might have heard of Vader Systems and a little familiar with that technology. Xerox now owns that technology, and we're really leaning into the expertise that Xerox has for ink jetting. So that sort of meshes with the jetting of liquid metal here. And now here's a video overview of the printer. It's a little marketing focused, so we won't spend that much time on it, but it does provide a good kind of overview of the printer itself. So here is the wire feed. It is kind of off-the-shelf welding wire, so that is an advantage we have here, where you have the simplicity of wire without dealing with powder. And this inkjet, or this head, is what I'm going to be talking about primarily, where we have our liquid metal, and the mechanism for ejection really happens here. This is where the magic happens. So as far as print head inputs, that video showed just really the liquid metal, but there are a few other things going on in that print head. Obviously, we have some heater power to maintain that liquid metal. So we are dealing with a pool of liquid metal in the print head that we are then ejecting and solidifies on the build plate. It's a little different than some of the other technologies. So some of you guys who are familiar with aluminum might be saying, wait a minute, that aluminum is going to oxidize very quickly. So in that print head, we do have an argon shielding gas. And what this does is it protects the molten aluminum from that sort of oxidation. That argon sheath also extends to the droplets when we're printing. Now, the heater power puts out a lot of heat, and obviously dealing with molten metal, that gets quite hot. So we also have some water going into the print head. It is a water-cooled print head to make sure that only the parts that want to be hot are hot. Otherwise, you end up with some melted bits. And then the key part here that we're going to be talking about is the pulse that comes from the system computer. This is the pulse that actually ejects the droplets. So we end up with a series of single droplets rather than a continuous bead. So as I said, the mechanism we use is called magnetohydrodynamics. It is a mouthful, and I am a metallurgist, not an electrical engineer, so I will explain it to the best of my abilities. But what we use is a magnetic field coming from a coil surrounding the aluminum, and that then forces the metal through a nozzle where individual droplets form. One misconception that people have when they hear magnetohydrodynamics is that the material we're jetting must be magnetic, but that's not the case. We use electromagnetic induction, so as long as the alloy is conductive, then we can use it with this mechanism. So here's the process breakdown. I'm going to go step by step and hopefully provide a good description. So on the left here, the first step is we're focusing on a single ring of aluminum inside the coil. So the coil is surrounding this already liquid molten aluminum. The coil driver, or the computer I talked about before, then sends a pulse of current around the coil, which, if you guys remember electromagnetics, this causes a magnetic field to form around the coil as pictured in the third step. Those two steps then sort of copy themselves in the aluminum itself, but in reverse. So the magnetic field is then going to cause a current in the aluminum ring itself, but going in the opposite direction. And that electrical current then produces another magnetic field also in the opposite direction. So then you end up with two opposing magnetic fields in the opposite direction. And what this does is it physically squeezes the aluminum and ejects a droplet. So you can think of it kind of as squeezing a tube of toothpaste or some ketchup. So that's how we start pushing the aluminum out. But we also found the key to get droplets on demand instead of a continuous stream is actually you have to turn off the pulse. So when you turn off the pulse, this whole process kind of reverses. And you have to keep in mind that these are on very rapid time scales. So when the process reverses, it actually pulls the aluminum back just a little bit. And this combination of pushing some aluminum out and pulling it back just a little bit is enough for the droplet to break off the meniscus, and we have a nice spherical droplet coming off of that. So that all sounds fine and dandy, but I did want to show that we can actually print parts with this. These are the kind of types of parts we would end up with. I think these are typical of the surface finish we get. And I just took some images of example parts, so pumps, fluid management, brackets, those sort of things. And these are just example parts. However, we do have a partnership with the Naval Postgraduate School, our first customer, and these are some of the parts that they are printing and evaluating. So since it is a first generation technology, you guys are familiar, it's going to take some time to verify the process and the mechanical properties before people are comfortable using it in structural applications. But I thought these were some nice examples. They're looking at how they could use it to help the US Navy. So light fixtures that break frequently, wrenches that go missing, valve handles that endure a lot of abuse. Those are parts you could kind of quickly print and have a replacement for on hand. Now, I wouldn't be any kind of metallurgist if I didn't show you guys at least a little bit of microstructure. So I did kind of want to talk about the quality of what we print. I haven't talked about what alloy we use, but it is an aluminum called 4008. So 4008 is the chemical designation for the welding wire. And on the right, you have A356, which is the casting equivalent of that chemistry. So these are chemically identical, but on the left, we have a microstructure example of what's come off of our printer. And on the right, we have an example of what comes out of castings. And these are both in the as printed or as cast state, so they have not been heat treated. With this 4008 aluminum, the primary strengthening mechanism is from the precipitation of silicon and magnesium. So these darker particles you see interspersed on either the casting or the printed part, those are the silicon particles. So you can see on the printed part, they're very evenly dispersed, whereas in the casting, you end up with these sort of globs of the aluminum matrix. So the fact that it is so well dispersed kind of lends itself to some strength in our application. However, I hinted at the fact that these parts are typically used in a heat-treated state. So when we do heat treat it, you can see that our microstructure coarsens itself, and this is very typical. Um, and it's still, very well dispersed, all the silicon particles. You also see that some of the particles have become more rounded, and this also lends itself to some strength. So as far as mechanical properties and physical properties, I would say that the surface finish is sandcast comparable. It's not the smoothest surface finish, and if you have critical mating surfaces, you might still have to machine those surfaces. But I think it is a pretty standard kind of surface. And then our density is greater than 99%. You guys are probably aware there's some nuance in with regard to density measurements, whether you're using Archimedes or CT scanning or image analysis, and they all agree that it's above 99% or 99.5, which I think is great for a technology that's really only been around for, just barely 10 years. Um, And then you'll see some tensile data. So on the left, we have a baseline for A356 sand casting from the ASTM standard. And on the right is what we've achieved in printing. Um, so this is still, first generation technology. We're still developing, but as a metallurgist, I'm pretty happy with these numbers. We're above the baseline. Especially the elongation is pretty good. We do, of course, see some differences between horizontal and vertical orientation, which I think is fairly standard for the additive industry. But of course, we are working to understand what drives those differences and how we might improve our printer to improve upon those differences. So overall, I think this is really a unique technology that's come a long way in a short time. And I'm very excited to see where it goes from here. So I'd be happy to answer any of your questions at this point. Um, but also, if you would rather contact me privately, I just put my email up there for reference. So thank you guys.
Thank you so much, Miranda. That was super fascinating. I'm always interested to see what the latest on the magnetojet technology is. So thank you so much. We do have a lot of questions, so let's get right to it. The first question in the Q&A tab, just a reminder, if you have a question, there's a chat tab, and then there's a participants tab, and then there's a Q&A, so you can put your questions in that Q&A. The first question is, what is the droplet size and the geometric resolution that you can achieve?
Yeah, so our droplet size is around 250 microns. So that's fairly different from the layer sizes that you might deal with in SLM or binder jetting. But what that does enable is very fast printing. So we're laying down a lot of material very quickly.
Excellent. Next question is, what materials other than aluminum have been tested with this system?
So we are still exploring new materials. Like I said, it's kind of a first generation technology, so there's some work that has to happen before we start exploring other alloy families. Since we are maintaining molten metal, the process does sort of naturally suit itself to lower melting point metals, which is why we started with aluminum.
There's a question that I don't understand. It's what are the considerations of X? I don't know if you understand that. If not, we'll just pass it on. And if you want to ask that question again,
I think that was like an example question of how to use chat.
Oh, good job. You figured it out. I couldn't figure that out. Okay, great. All right, next question is, are there any residual stresses after printing? And how do you support the part on the print bed?
So there are some residual stresses, but since we're printing and cooling on the print bed itself and the print bed is heated, we found that the residual stresses are fairly low, low enough that we typically don't have to concern ourselves with distortion when removing from the print bed. And I think the second part of that is how is it supported on the print bed? Typically, we print directly onto the bed itself, and we can print 45 degrees, I think, without any supports, and our supports are still being developed. So we try to print without supports, of course, if we can, and if we can't, then we're still kind of improving our supports. Oh, Amy, I think you're still muted. Sure.
How much post-printing cleanup are you doing? Are you doing machining?
Yeah, so usually we don't have that much cleanup to do. It's just been kind of the applications that we have been printing don't require it right now. I'm sure if we had, critical mating surfaces or tolerances that were outside of what we could hold with the printer, we would be doing machining or polishing or things of that nature. But right now, our post-processing is pretty much limited to the heat treatment. I don't think I've discussed part removal from the build plate yet, but basically what we do is it's printed onto the build plate, and then we put that build plate into a cooling tank, and the differential and thermal expansions between the build plate and the part that we printed allows it to just pop off. So it is a very simple part removal process. You don't have to worry about sending the build plate to be machined or resurfaced or anything like that.
Excellent. The next question is, would the sisal droplets not oxidize while you're printing the next layer?
Yeah, that's a very important question. And the answer is that the argon that is circulating in the print head is also kind of used as an argon sheath around the jetting stream. So it's similar to what happens in welding, where welding also uses a sheath cover gas to protect the metal from oxidizing.
Perfect. Do you foresee 6000 series aluminum being material Xerox could provide? And if so, what solidification issues do you expect?
Yes, 6000 is a popular question, of course. I think everybody wants 6000 series aluminum, but I can't really talk about what's under development right now.
Right. Lots of questions here, so this is great. What's the minimum wall thickness?
Gosh, the minimum wall thickness, I'm not sure what we publish in the design guide right now, but I'm pretty sure it's about 0.2 millimeters. Um, Whoever asked that question, if they want to email me, I can get in contact and send them the design guide if they would like.
Perfect. And then what's the maximum size of printable parts?
I think our build plate is 12 by 12 right now, although we rarely use that large of a space while printing. And then height-wise, I'm sorry, but I'm not sure. I can also send the design guide to you and say what our current recommendations are.
All right. Yeah, still lots of questions. It's great. So what advantages does liquid metal printing offer over powder bed?
So I think I touched on one of them, but we're very fast compared to powder bed. I started in selective laser melting, and it was kind of shocking to me how fast we were, but we could, print some parts in 20 minutes that I think would have taken hours on an SLM. So it is very fast. We're ejecting those droplets at a rate of 30 or 40, 300 or 400 hertz, excuse me.
Do you expect any challenges in printing taller parts, i.e. achieving precise droplet deposition when the part grows vertically and given that the bed is moving?
Yeah, so I believe we're working right now to enable taller parts. Right now, I think a common problem when people try to print taller parts throughout the AM industry, and one that we're seeing as well, is maintaining part temperature from the build plate to the top of the part, because our build plate does provide heat to the part.
Definitely. Okay, so what advantages does liquid metal printing? Okay, I think we already had that question. How about this one? With the drop size of 250 microns, what is the typical resulting layer height and pixel size? I'm guessing that the pixel size is not uniform.
Yeah, so as the droplets fall, they kind of splatter and spread out a little bit. I would still say that they maintain their circular shape, um, but typically our layers are around 0.24 millimeters, I think, so very close to that 250 micron droplet size.
All right, last couple questions. What material is used for the metal container and nozzle?
Oh, I'm not sure I can talk about that. Um, I would say if you're interested in that, then, containers for handling molten aluminum have been around for a long time, and probably the casting industry has some ideas there.
Awesome. What environmental controls are required for your machine?
So our machine is kind of open air. Really, all we require is a dewar of argon to provide that circulating argon in the print head as well as the sheath. But there is no sort of like vacuuming down process or purging process in a chamber similar to what you would see in SLM. It's only that argon sheath.
Great. And you had already touched on the mechanical properties, how they vary in the horizontal and vertical directions. I don't know if you wanted to bring that slide back up or not. That's totally fine. Let's see. But yes, I think that the answer to that question was yes. And then the next question was, how many materials can be used in the machine?
So right now we only have one material released, which is that 4008 aluminum I was discussing. But I think, keep an eye on the news. We are expecting to release more soon.
A couple questions you may not be able to answer live, but how many customers do you have utilizing the machine today? And then what is the cost of the machine?
Yeah, if you'd like to know the cost of the machine, I would have to put you in touch with sales. But I can say that it's comparable to the cost of other sort of similarly sized metal printers. And then as far as customers, the only customer I can talk about I mentioned, and that was the Naval Postgraduate School. Other than that, all I can say is, again, keep an eye on the news because there are some deals in the works.
All right, we'll call this the last question. Thanks so much for answering all these.
Of course, I'm
okay.
glad people have questions.
Yeah, for sure. Whoops. Okay, so we have two now. Do you ever run into problems with satellite droplets at the nozzle or splashing on the substrate?
So first, satellite droplets. Yes, if there's a problem with the jetting, then we do kind of see a secondary stream, and that's an indication that something needs to be adjusted on the printer. But typically only happens when something is kind of out of whack with the process. And then splashing on the substrate, I don't think we've seen that. It could be possible. I suppose I've heard of incidents of what we call bouncing droplets, but that's typically on the first layer. And again, it only shows up when something is kind of out of whack with the printer. And if we saw that, we would have to fix something.
Gotcha. All right, let's conclude the Q&A. Thank you all so much for your questions. If we didn't get to your question, feel free to reach out to Miranda directly. And thanks again, Miranda, for this really exciting talk.
Sure. Thank you, guys. I was really happy to participate.